Hey everyone, in this video I'm going to show you how to find the determinant of a 2x2 matrix, as well as how you can build the inverse matrix. So in our last video we did multiplication of matrices. This is the beginning step for how we effectively divide with matrices. Like I said before, there's no real division of matrices. We use a form of multiplication to do it. But what we need to find is the determinant. Now the determinant is just a value that can be determined a bunch of different ways, but I'm only going to have you do it for a 2x2 because there's a really generic formula. So in a matrix with A, B, C, D entries, we can find the determinant by doing A times D minus B times C. So I'll do that again because I like to show you sort of like more of an arrow, A and D minus C and B. So I kind of think of it like it's kind of swooping one diagonal and then up through the other. So let me show you how we do it here. So I would do 3 times 4, which is 12, minus 11 times 1, which is 1. So the determinant of A is just 1. Okay, so again, we can do it here. So 4 times negative 3 is negative 12, minus the value of the other diagonal, negative 21. So negative 12 plus 21 equals 9. So the determinant of this matrix would just be 9. Okay, one last one. So 5 times 6 is negative 30, minus 3 times negative 10, which would be negative 30 again. And so here we get a determinant of 0. Now this actually has a really special property. If a matrix has a determinant of 0, that means it's what we call a singular matrix, meaning that there is no inverse to this matrix. So the previous ones all had an inverse that existed, but this one cannot. Now, one quick way to kind of show you how to tell if it will be 0 without actually doing the multiplication, if you look at the first column and compare it to the second column, do you notice that it is a scalar, a times negative 2 scalar? So if any of the rows of the columns are exact carbon copies of the other, that means it's a singular matrix, meaning there's no inverse. So the inputs all have to be unique. So now how can we actually do this? Well, so if we have a function or a matrix, A, B, C, D, if we have the determinant, well, we can construct the inverse matrix by doing 1 divided by the determinant, and we do a little bit of rearranging here. So D and A get switched, and B and C both get negatives. So once we have that, then we distribute the inverted determinant into all those values, and that would be our inverse matrix. So here are the matrices where we determined the determinant previously. So now that we have that, let's find the inverse. So the inverse of A is 1 over 1. So remember, this value here is the determinant. Now we swap A and D, so 3 and 4 get swapped, and the other two cell entries just get a negative. Now this one's a really easy one because it's all going to be whole numbers, because really this is just the value 1. So the inverse itself is just all that nice swapping. Now in the other one, we found the determinant was 9. So to find the B determinant, the inverse, I would do 1 over 9. Then I have to distribute into, so again, we switch top left, bottom right, and we change the signs of top right, bottom left. Now I apply the 1/9 factor to all of those. So 4 over 9, 7 over 9, negative 3 over 9, negative 3 over 9. And then we can reduce those, 4 over 9, 7 over 9, negative 1/3, negative 1/3. So that would be the determinant here. Now, if you're really intrigued as to why that these are important, what I'd recommend, and then you could kind of do this off to the side, is do a little matrix multiplication of A and its inverse, as well as the direction A inverse and A. Remember that the order does matter, but with inverses, they will not. And you'll see what you get. Whether you do this with either A and A inverse or B and B inverse, you'll get the same answers every time. So there is a reason why we want to do inverses. All right, Well, I hope that was helpful, and I'll see you in the next one.